So yeah, so as Beat mentioned, I'm CEO of Active Group, and we've been doing industrial projects using functional programming for the past at least 10 years. And we've always believed that obviously it's the right idea to do software development and industrial software development using functional programming. And we talk a lot to people who are not doing functional programming, and they sometimes just don't seem to get it, right? And clearly that's their fault. Right? Our brilliant ideas just bounce off their opaque brains or something like that. But really, over the past 2 or 3 years, I've been trying to do that more consciously and been realizing that there's just a lot of things that we have not communicated properly about functional programming. So if you believe functional programming is a great idea and you're talking to other people who just don't seem to get it, you might have to think, or it might be beneficial to think about the things that you're communicating. So I'm going to do again a keynote I did for Trends of Functional Programming conference in Oxford a couple of weeks ago. Every talk is kind of a performance, so this gives me an opportunity to do a little personal note. If you're interested in performances, so I'm also in a different life. I do theater, and we're actually playing in Berlin 2 weeks from now. So if you're in Berlin 2 weeks from now, we're playing Heiner Müller's quartet that is pretty much officially part of the German literary canon. If you happen to be in Bremen on April 12th, you'd be welcome to come here. It'd be wonderful to have some audience there. I've got some postcards up here. So back to this, and I promise this has nothing to do with functional programming, except that the lighting system is my PhD thesis implemented using functional programming. So anyway, so functional programming, why is it a good idea? Right? Why would you tell anybody to use functional programming instead of whatever it is that they do, object-oriented programming, Java, or whatever? And well, functional programming is programming. Programming means you build software, and ideally your software system is going to fulfill requirements. And you might think, well, that's obvious, right? Fulfilling requirements. Right? But then you go to the big conference on functional programming, ICFP. So this is ICFP 2024, the International Conference on Functional Programming. And it goes abstracting effect systems for algebraic effect handlers, abstract interpreters, Coq mechanizations of JavaScript regular expressions, almost sure terminal. Nothing here refers to fulfilling requirements. This is not the whole program, right? If you look further down the list, you'll actually find some papers about fulfilling requirements. For example, one of the distinguished papers, so I was on the program committee and I voted for this paper also to be a distinguished paper. So this is about a technique that is actually for fulfilling requirements. But what are those requirements? They are implementing type checkers and automated theorem provers, right? And so maybe we might start at talking about how to fulfill requirements that are in software systems that people actually want to write and develop. This is not completely absent from the body of literature on functional programming. So one of my favorite papers is this one, How to Write a Financial Contract. That's from ICFP 2001, so now well over 20 years old. And something that we use as an example in our architecture training. And the thing is, right, whatever it's about, right, it's about building complex financial products, doesn't really matter. But like on page 1, right, it says, well, here's a bunch of requirements. What we want to do is we want to model complex financial products. And then it says, well, obviously, in order to fulfill these requirements, you should build a combinator library, right? Obviously. So this was folklore even, well, now 20 years ago, 25 years ago, going on 25 years. But you would be hard-pressed to find literature on how to build a combinator library. There's actually one book now, which came out a couple of years ago, but it certainly was not available back then. So the underlying assumption, Simon Peyton-Jones's underlying assumption was everybody knows how to do this. Isn't it obvious, right? And even though there's many examples of combinator library, there's no published book on a methodology on how to do that, right? And you might contrast that with a large body of literature on how to build software that fulfills requirements, right? On things like software architecture, domain-driven design, on collaborative software design, on visualizing software architecture, on design patterns, and I could cite a lot more books here. Nobody's going to say, well, there's a lambda there, right? So there's that one book that says, actually is like software design for flexibility. that really is about fulfilling requirements, but it uses schemes, so it's completely irrelevant for industrial applications.
There's a TypeScript version.
There's a TypeScript, really?
Yeah,
Okay.
a JavaScript version.
A JavaScript of this book. Oh, okay, they switched. Okay, that's new then. So maybe this is it now. This is going to take us. Well, you can try to pretend that it is. Yeah, certainly. Anyway, so let me talk a little bit about what it takes to build software, right? So if we want to build software systems, we should maybe think about the fact that we're building software systems for people occasionally. So that we should fulfill human requirements rather than requirements that come out of some formality, some chain of formal arguments that you're making for research. So they should make somebody's life better. So I'm not going to talk about blockchain much. And it's, well, at this point in time, it's programmed by people. And so what it really takes is we need to connect the requirements to the actual software product that implements them. This involves programming in the small. And it's kind of folklore that programming in the small is something different from programming in the large. So if your software lives for a long time, maybe you're going to have to do things that you're not thinking about when you're just writing your little program. And then there's all kinds of human activities around this. When we talk about requirements, it's worth mentioning that not just in functional programming, but specifically in functional programming, we usually think about the functional requirements, right? But there's a lot of other kinds of requirements that are worth taking into account. So here's Gernot Starke's taxonomy of software system qualities, and then you can formulate requirements on all of these qualities. So you might want to have things like, apart from suitable, which is, this one is about functionality, you might also have requirements like safety or security, reliability, efficiency, usability, things like that. So really, we also need to think about those things. So I mentioned that because at the last ICFP, one of the keynotes, right, was utterly, I think it even had like a title that mentioned requirements, but the keynote speaker was utterly unaware of anything other than the functional requirements. So maybe you're going, yeah, duh, but I'm just saying that because it needs saying, right? And so for functional requirements in programming in the small, actually, we're doing pretty well in functional programming. So there's not just do we know how to do it, but there's also ample documentation on how to do it and how to teach doing it. Primarily the work pioneered by Matthias Felleisen and his group on how to design programs. And I can't recommend enough that you look up this book, which is also completely available online. If you're here and you speak German, or you want that for a German speaking audience, well, I guess I can plug my own book, which is not quite the same book, but uses the same kind of methodological approach to teaching how to program. So we know how to do that. We know how to do it, and we know how to teach it. And really, programming in the small in functional programming is about designing data and functions that operate on that data. So the next bullet point here was programming in the large and in the long. And at least for programming in the large, there's ample evidence that functional programming is at least suitable for doing that. So once upon a time, there was a sequence of international workshops called Commercial Users of Functional Programming. I think the last one was in Oxford. I think the program here is from 2017. And that has all kinds of, if you look here at the list, it has all kinds of applications of functional programming on genomics, on set-top boxes, on implementing Zen client, on medical software and power grid software. We heard about power grid software earlier this morning. So there's all kinds of industrial applications, right? Most of these, I should qualify that, right? Most of these projects had not lived for very long, though. They were large, but they had not lived for long yet. And some of them, I'm sure, have not survived. So anyway, so we know how to do the large. Maybe we know how to do the long. I certainly think so, but again, there's the question of have we documented on how we did it, right? Then there's all these human activities, and if you look at sort of software architecture and software design works, and also conferences in the space outside of functional programming, then there's lots of events. So this is from the Como Camp event on collaborative software modeling. And so there's all kinds of events that really focus on the human side, right? And you'll recognize it because there's post-it notes, right? And not like Greek letters on slides and things like that in the background, right? And well, if you look for this, in the context of functional programming, again, well, there's not that much. And all the literature on this, things on agile programming, on event storming, on domain-driven design, domain storytelling, is all firmly from the object-oriented programming community. And this is all valuable stuff, right? But neither have we adopted it, nor have we kind of produced as a so I'm always saying we, right? If you're object-oriented in this room, I don't mean you. But so I really, in my life, you think it's funny, but I really have never done serious object-oriented programming, which is part of the problem, right? So there's lots of stuff on the human activities, right? We have not, or nobody has connected them to functional programming yet. So if we're kind of trying to make a checklist, well, first of all, do we know how to do it, and have we taught it, or have we communicated it, right? Then, well, connecting requirements and software, sort of in the larger sense. So for some small sense, we've documented that in the form of the design recipes, but as far as the other requirements are concerned, the other kinds of qualities that you can have in a software system, not really. Programming in the small, we've got that pretty well covered. It's great. Programming in the large, well, it's at least documented that it exists, but have we documented on how to do it? It's not that there's no books, but there's very few books on like software architecture or software design, and I just showed you one, and there's like maybe 2 or 3 others. And on human activities around this, zip. Right? So maybe we need to think about these things. Maybe we think that human activities, somebody else can take care of that, but really, humans, but we really shouldn't. So let me backtrack a little bit on the programming in the large and the long. After all, software people have been thinking about this for a very long time, right? And one of the first books on this is this book, the Green Book. Has anybody seen this? Yeah, one person here has seen the Green Book. Yeah. Yeah, so one of like the handful of books that you can identify by their colors, by their color in computer science. So here's the Green Book, if anybody asks you, right? It's from 1979, right? So this is in the days of like paper tape and things like that. And what the authors did is they tried to figure out, now imagine that 79, right? Not very much software had been written yet. So really all that methodological knowledge that we have now, they didn't have it. And so they thought about this from first principles. And so they thought about, well, if we have a software project, where does all the money go, right, over the years? And they found out something that seems obvious now, but certainly wasn't obvious then. Well, usually a software system, right, a couple of requirements get written up, and a first version of it gets implemented and deployed, right? And then the system gets changed because new requirements arrive, the old requirements change, and not very well. I guess surprising. It is kind of surprising that we really need to spend a lot of money on changing the system rather than deploying it and implementing it for the very first time. All the money goes into changing it. And so we really need to think about what is it that makes a software system economically efficient to change, right? So, and this is particularly relevant because here is from a talk by Markus Hauer, who was at Baum last year, gave a talk at OOP a couple of years ago. And here's a list of the different qualities according to the ISO norm on software qualities. And he did a survey and asked people, well, at what point during the software lifecycle does what quality come into focus, right? And not surprisingly, the first one, the functionality, is the one that people think about first, right? We want to do the software system. I click this button, that happens, right? And then a little bit later, aspects like reliability, usability, performance, security come into focus, right? And now the quality that has to do with changing the system is down here, maintainability, right? And you'll notice it's pretty far down the list, right? And so if you've written a lot of software by the time that you get here and you haven't thought about maintainability, it might be too late, right? And that's why in object-oriented software, people talk a lot about refactoring and various other things that I'm going to get into, right? Also, the software architecture community really is pretty funny about a couple of things. So here's one of the major books on software architecture in practice out of CMU, the Software Engineering Institute there, that says, well, so architecture is about software in the long and in the large, right? And it has this thing, well, remember, functionality is the thing that comes into focus first. And they say, well, functionality has nothing to do with architecture. I think that's crazy. but it tells you a little bit. If you think that's crazy, does anybody think that's crazy? That's odd, right? If you think it's crazy.
Is there an observation on their part, or is this like an exhortation?
Both, I think. Both. There's a page-long rant on this subject actually in the book.
Take the word determine. I mean, pedantically, determine means, given the functionality, you absolutely have only one option for the architecture. So in that case, it's correct. There are multiple options for architecture for given functionality. On the other hand, there's obviously a relation between.
Yeah, but this is the case for every other quality as well. So I would say. Anyway, the main thing that I want to point out, I don't really want to complain about this, but if you think this is strange, right, it tells you how big the gulf is between you and this, right? That was my main point anyway. So I'm going to leave that one alone for now, but we'll get back to it later. So back to the Green Book, right? What they said, well, they determined that, okay, so we need to keep the system changeable in order to not spend a whole lot of money on developing it. And then they thought about, well, what makes a system easy to change? And then they came up with this term that we know about today, which is called coupling, right? Which is the interdependence between different parts of the system. It's a little unclear where the term coupling really originates. It might be from this book. Again, the book is from '79, but people had been thinking about that phenomenon even though they didn't call it that even before then. So David Parnas, if you've ever read anything about software architecture, this is the classic paper on modularity from 1972. And Parnas was thinking about how to split up your system in a way as to get the lowest amount of coupling possible, right? And so he kind of did a little study, alternative study of two different ways to split up an application. And there's this funny thing, and then he said, well, I mean, ideally, so maybe coming back to this point that functionality does not determine architecture, so he did one version where he split up the modules according to functionality, and then there's another one where he did something different, where he thought about what decisions am I making as I'm designing the module structure of my software. And he said, well, really, the better way to do it is to have one module hide a design decision. It's particularly a design decision that is likely to change or that it was difficult to make, with the aim of making it easy to change later. Okay? That is worth mentioning because I invite you to go to a software architecture conference, and that is going to be full of people who tell you that you really need to think hard about the super important, super expensive decisions that you need to make at the beginning of your project, right? So as far as the architecture community is concerned, I think they've given up on this, right? More than 50 years later, right? So, and so there's something wrong here, definitely. So, I mean, you could argue that this was never relevant, but I don't think so. And I think you can see that it's wrong by, maybe you've noticed a slight shift in terminology in recent years, right? In that there's a new term, there's a new term on the block, which is called the modulith, right? So the modulith is, so refers to the term monolith, of course. It's a wordplay on monolith, and a monolith is just one deployment artifact that is part of your software system, right? And so they say, well, the monolith, salvation for the monolith, and if you kind of read on this, I'm going to get to the microservice thing here in a moment, but you can see the basic assumption here is that the monolith is always unmodular. In other words, as sort of the larger software development community, obviously we haven't even figured out how to do modular, like basic modular software, right? And you wonder, well, but people have been developing these giant systems, right? How did they do that, right? If the monolith is always unmodular, and the answer is microservices, right? And again, I don't want to dunk on microservices so much, right? So what is the idea with microservices? You split your software system into multiple deployment artifacts, into multiple monoliths, okay? And if we keep them small enough, maybe it's not going to matter so much that each individual one is unmodular. We can just throw it out if we don't like it anymore. Now, it seems a pretty drastic step though, right? Your pleasant monolith where you could use all the programming language features to connect the parts of your software, you now have a distributed system. And maybe you have a distributed system with a gazillion components that nobody knows how to start up anymore if it ever goes down. And so it seems like, I mean, it seems really sad, right? If it's a worthwhile trade-off to go this route just because you're like, oh, we absolutely don't know how to do a modular monolith. You know, I mean, it's not just the development effort that goes into this, it's the runtime effort, right? Every single, you know, little thing that you do goes through a network connection, CO2 emissions, whatnot, and so on. So that seems pretty sad. And again, if you're from the functional community, you think, well, we've got all those nice type-based interface languages. We've got things like the OCaml module system. We've got low coupling due to immutability, and you'd be right. So we know a lot about, I'd argue, we actually know a lot of things about doing modular monoliths, right? Immutability, I think, is the biggest force here at place, right? It's maybe the easiest to grasp, but gives you the best leverage. Immutability gives you the ability to to establish good and non-leaky abstraction boundaries. We have all these expressive interface languages. We're getting to the point where we can put effects in our interfaces and further sort of clamp down on controlling these things. And so, so this gives you something that I argue in a lot of cases gives you something that my coworker Marcus calls decoupled by default. And this is really what we want, right? We want to develop software where we don't have to like try extra hard so that our software stays modular, but instead we want sort of the default model, the default mode for programming. We want it to produce software that then is later efficient to change, right? And so we know how to do this. Obviously, we haven't communicated it. And that the first time this became clear was, I think now 6 years ago when we started designing, and Nicole Rauch and I started designing a curriculum on functional software architecture for the ISAQB, which is an organization that does a lot of sort of classes on software architecture, when we realized there was not really a comprehensive reference on how to do it, right? How we use all those great techniques for producing decoupled software in implementing real systems. And so there's actually a significant amount of original work in this. And we've refined this over the years. And so I'd like to propose sort of a blueprint for functional software design that in one version or another, us people who were involved in industrial functional programming have been following, right? And if you're doing industrial functional software design, things might differ in details, but I think there's a lot of things here that hopefully you have in common with us. So I think what's relevant is that functional software design is fundamentally a bottom-up technique. It's not because it can't be top-down, but it's just because the way we've been practicing it. And I'll have an example in a moment. I think, again, through the way that we've been practicing it, we have always been used to starting with the functional qualities, with the functionality of the system, right? And if you talk to other software architects, remember, they will tell you functionality has nothing to do with architecture, and you're going to have to make your architecture up front. And I think we should proudly stand up and say, no, this is exactly how we should do it. We should implement requirements as we get to know them. At the first one, once we get to know are the functional requirements. Another principle is everything is data. And a seemingly minor point is that we do data modeling with sums and products. And also what plays important roles is our use of abstraction, our use of combinator models. Again, you might think, doesn't everybody do this? No, they don't. And the use of mathematics. So I'll try to elaborate a little bit and hopefully not bore you too long on this. So maybe here's an example on bottom-up modeling. So here's a classic paper, also I think about 25 years old, from Conor Elliott and Paul Hudak on functional reactive animation. So this is the genesis of what today is called functional reactive programming. So they wanted to do like reactive graphics, right, where things move around, and it would also react to, if it were like a video game, it would react to actions of the user and things like that. And you could approach this kind of top down and saying, well, I want a very simple animation, but I want like the whole thing. I want it to be displayed on the screen. I want it to react to the actual mouse, hook up everything, but do something very simple. And what they did is they did something else. They did something called, down here, modeling first. So they first created a data model for reactive animations. And only when they had that data model did they produce to actually put things on the screen, right? And that's very typical in functional programming circles, in that we would create a model, we would think about its properties, and we would put that in the software before we created an entire complete software application around it, right? So the top-down or bottom-up really refers to the sort of the all the layers of your application, rather than sort of doing like a function top-down or bottom-up. There, it doesn't really matter, and you can mix and match that in functional programming as well. So modeling refers to, in this case, representing an animation as data, right? And this is not clear that you would always do that, right? You could easily imagine that an animation would be represented like by a method in your program that keeps changing the colors of the pixels on your screen, right? This is different from representing it as data in sort of a declarative fashion. So data modeling, and the thing in functional programming used to be the distinguishing characteristic of functional programming that functions were also data. So now we can kind of we can re-emphasize this, right? So functions are data. Well, other kinds of data are data too. And then we tend to think about data in terms of products and sums, especially if you are using a functional language with algebraic data types these days, right? Where you have one construct in your language, and it gives you a sum, and each individual sum is a product, right? And this is like second nature to functional programmers using functional languages. But we recently, so Stefan Wehr, who's also here, we're both in the foundation training group of the ISAQB, so we're doing the basic architecture training, and we just recently put in a new learning goal on data modeling. And we said, well, software architects understand the difference between sums and products. And that resulted in a little shitstorm, because there were a bunch of architects coming out of the woodwork saying, well, I've been architecturing software, for all my life without knowing this. So how could this be relevant? And they're right? If you look at a lot of software out there, if you really look, you will find out that it uses mostly only products, right? Often motivated by the fact that there's a relational database and things like that. You will find like nullable fields maybe, right? But this fundamental use that you think, this thing in my domain, it could be this, and then it's structured like that, or it could be this other thing, and then it's structured differently, is completely is just unknown in a lot of circles, right? And then Stefan and I subsequently wrote up a blog post on this, which was like the most popular blog post ever on our blog, which has been running for over 10 years now. So that seems to be relevant, right? And so data modeling, I really need to mention this, because we think, well, isn't everybody doing, the object-oriented people, aren't they doing the same thing? No, they're not. And I say data modeling to distinguish it from objects. So really, the object-oriented community models different things. There's no commonality there, right? Just to give you an idea, here's this classic example. If you've seen a talk by me, you've seen this, right? So this is about animals on the Texas highway, and there's armadillos, and then there's rattlesnakes and something like that, right? And the armadillos get run over on the highway, right, by the those big-ass cars that you see in America, right? And when you ask the object-oriented people to kind of design the software structure for this, they'll usually come up with something like this, right? There's an interface animal, and it has a method run over. It has conspicuously return type void, right? And maybe on a nicer note, you could also feed the animal, right? And well, as functional programs, we immediately think about, well, obviously run over is doing something dirty behind the scenes. This clearly can't be functional. I'd also like to draw your attention to the fact that sort of, thinking about the sort of esoteric nature of it, it seems like the animal runs itself over, right? So there's not this notion of like the car is doing it. So every object basically is responsible for changing its own state, right? And so this notion that some other thing might come along and do that is more difficult to get at in this model. Let's put it like that, right? And of course, in functional programming, we would have more like a data type called animal, and we would have a function that, and we really think about this differently, right? Whereas the object in the object-oriented scene that you saw earlier really is supposed to represent the animal. This one is a representation of the state of the animal at a certain time. And in this function, right, you see the state before you ran it over and after you run it over, right? I always think about this like, you're sitting in your car, right? You're seeing that cute armadillo in the distance, right? And your phone rings, you get distracted, and you kind of go, ooh. And then you look out the back window. There's the dead armadillo, but you remember the cute little live armadillo from 5 seconds ago. But your heartless object-oriented software has forgotten. Okay? Anyway, so this idea of this object-oriented idea that the world consists of isolated objects, right, which is very important to object-oriented software architecture, just doesn't correspond to the real world. And we should talk more about that. I think we're not talking about that enough. I think, one example that I think I stole from Rich Hickey is this one. So imagine you're watching a soccer game, right? You're going in, right? And there's lots of moving objects that you're noticing, right? There's people in the audience, there's, of course, the players, there's the ball, there's the referees, and there's all kinds of things that are remote. How would your object-oriented approach learn of what's going on in the game? Honest question? 3 seconds? Huh? Yes, but what is the object-oriented pattern you would use for this? The what? The referral strategy? Okay, everybody else says the observer pattern. Sorry, so that seems good, but most people will say the observer pattern, which is you register with all those mutable objects that you're interested in, you deregister when you leave the stadium. And I think it's kind of obvious that things don't work like that, right? Indeed, what really, very roughly, the human brain kind of takes a snapshot picture of what's going on, and then takes another one, and then infers the state changes from the differences between those pictures, right? So, anyway, so getting back to the architecture, right? So very roughly, I think in functional programming, the way we should handle architecture evolution is, right, we start with functionality, which is the set of requirements that come in first. So we model the domain with data. We implement functions that operate on that data that correspond to things that go on in the domain. And then because we've implemented things that are decoupled by default, it's not so hard to make the required changes to achieve other quality-specific requirements, right? And so really, this low coupling that you get in functional architecture gives you sort of a correspondence between the sort of conceptual size of the change to how much it costs to implement it, right? Not always the case, but that would be the ideal. And I think we're doing far better at that than the object-oriented community. Let me talk a little bit about abstraction, right? This is a very generic term. I'm referring to something very simple, right? You have two things, right? And they differ in like details. For example, the color here. And then what we do is we just kind of, well, ideally in functional programming, we just wrap a lambda around it and we abstract over the color and everything else is the same, right? And I think in functional programming, we think of abstraction as an obviously good thing, right? But recently I did, Martin was there, I think you were there, right, at OOP? I kind of asked the audience composed at OOP, so audience composed of object-oriented people, and I asked them, abstract or don't abstract, right, at the beginning, right, without context. And most of them said, well, no, don't abstract, right? Because, and if you ask them why that is, and they say, well, abstraction often results in sort of multi-layered class hierarchies and deep object hierarchies and things like that. And you kind of go, what? And we haven't talked about this, right? Again, we haven't talked about this. What we mean, instead we're kind of go like, well, you poor losers, you can't do abstraction. And that doesn't really work as a marketing strategy, right? Let me talk about combinator libraries a little bit. So it is true, combinator libraries are something we should all be thinking about, basically, in every not absolutely trivial modeling problem, right? We should think about doing a combinator library. But remember, if you don't have products and sums, you can't even think about combinator libraries, right? And combinator libraries are, properly done, are really a systematic abstraction process, right? And they're very suspicious to the object-oriented and the domain-driven design people. But they're really good because they meet functional requirements, they facilitate communication, you can really kind of reflect your improved understanding back to the domain people. You can decouple a representation from behavior. You can think about semantics. And if properly done, right, they can slow down change, right? If you don't have abstraction, it means every little new business requirement requires you to make like a significant change to your software. So that's great. That's why these things are great, and we should talk about that rather than like it's obvious. Also, of course, the functional programming people are all like these, monad nerds, right? Why is this abstract nonsense? Why is it a good idea? What would you think? Huh? But why is it useful? How come? I mean, why that? Right? Why not go to the chemistry people? Probably also a good idea. But why is it the case that stuff from a branch of mathematics, really called abstract nonsense, is useful in mathematics? Right? What is it good for? Right? Yeah.
Because of composition, right?
What?
Put things together.
Yeah, why is that a good idea?
Smaller parts.
Why is that a good idea?
Because you can understand the smaller parts.
So, and then we're getting into the sort of, then maybe we can move on to discussion about requirements. But again, you would think, well, why do I need, well, maybe the other question then would be, why do I need mathematics to talk about this, right? And why the lambda calculus, right? Somebody earlier quoted Phil Wadler today, who said, well, it's been around for 40 years, so obviously it's going to be good, right? I mean, the lambda calculus was invented before computers. Why is the lambda requirements, ... lambda calculus profit? Why does that happen? And I'll tell you why. So this is my personal SOFA theory about this, is that it contains so mathematics is a collection of brain patterns for thinking, right? Because we don't put in our software the actual domain, we put in our software how we think about the domain, right? And so it's not anything that goes into our software. It really is restricted by the ways that humans like to think. And human brains like things like symmetries, maybe they like things like compositions, even if they don't know it and if they don't know all those funky terms from category theory. But every kid knows the concept of associativity, even if they don't know the term. I mean, literally, you can ask kids in 3rd grade, and they will explain that the parentheses don't matter, right? So anyway, I'll wrap up. So really, this is something that we should be aware of. Again, it seems very esoteric, but if you talk to the object-oriented people, they talk about constructing software in terms of representing the thing in the domain. And there's no intermediate step of, really only represents the way I think about the domain. And again, immutability helps, and so that's all good. Anyway, so, I mean, one step would be to just communicate what we have, right? That would help to communicate better, to write a bunch of books, speak at more conferences, have more people than just me speak at those other conferences. And my coworkers. So that would help. There's still a couple of things missing, I think, that we should be working on in the functional community. One of them is, so domain-driven design is fundamentally a top-down technique, and which is why it's fundamentally different from functional design. And despite lots of, I'm sorry, Marco, but lots of people who say, well, they're a good fit, they really aren't. Functional design and domain-driven design are fundamentally different ways of going about doing software. We should think about, do we need specific ways to visualize and document functional software architecture, right? How do we communicate with stakeholders, write a bunch of books, and just do more cross-pollination and not just talk at the object-oriented, clueless people, but also listen to them. That's it.
Thanks for the talk. Questions?
Yes, thank you very much for your presentation. I have a small question. I totally agree with the fact that the Gongo for book is a long complaint about if only you had lambda and modules. But when I used to write software, I think that codebase is extremely better than regular functional programming approach for using any social type, because just typing with abstract type is not very usable. It's extremely verbose and configuration hard.
Yeah.
And I think that objects are very good for external configuration. And I think that for me, the perfect language will be probably modular, having an OP language expressive
So partly, definitely. So
Thank you very
yeah,
much.
I mean, it's. I mean, I should point. I mean, let me point out the really concrete thing, right? Is lots of functional languages have not very good module systems,
Yeah.
right? And this is relevant because why is the monolith unmodular, right? Why is that, right? If you look over programmers' shoulders, how does it get to be that way? And one reason why it gets to be that way is that in modern IDEs, every single thing in your entire deployment artifact that you have is instantly accessible. So it makes it very easy to have like a cable, a red cable from that far distant, distant corner of the system to your other corner, and then everything gets connected, right? And the same is the case, sorry Haskell people, if you've done software reviews on Haskell programs, Haskell is exactly the same way, right? And so really, and this really is what the OCaml or the ML community has thought about this. Again, they have done it. I mean, especially the standard ML community who came up with this approach of doing module systems have done the absolute worst job of communicating it. But if we talk more about how that enables breaking up the monolith, that would be a total win, right?
I think that it's true in the object-oriented side.
Mhm.
It's because more of mainstream language
Mhm.
have very bad object model, and
Mhm.
maybe it's not related to object.
Yeah.
In statically typed language is very nice
Yeah.
with good properties, but just that Java is not very interesting, and it's
Yeah.
a very sad language.
Yeah. Yeah.
Other questions?
Yes.
Yeah, I would be interested in the reasoning why you think that domain-driven design and functional programming are a bad match. Or maybe I got you wrong. Maybe it's just not a good match, but...
No. Well, let me qualify that a little bit, right? So you can do domain-driven design using functional programming, and that's a good idea. So that will immediately make your domain-driven design better, right? But functional design, the way that we've been constructing software, right, is just something completely different from domain-driven design. And one of the fundamental mismatches is the fact that domain-driven design is fundamentally top-down and functional design is fundamentally bottom-up. They can be, I'm pretty sure there can be a good synthesis that combines the best qualities of both, but I don't think it's been done, first of all, and it's not as easy as I thought.